Good morning, Nasruddin.
Sir, good morning, sir. Can you able to hear me, sir?
Yeah, but don't call me sir. Yeah.
Yeah, okay, Karthik,
Yeah.
sorry.
Your paper ID is 265, right?
Yes, sir, two paper.
Two papers.
Yeah, 225 and 265.
Oh, 225 also. Okay, got
Yeah,
it.
yeah,
Yeah. Yes. 1 second. Yeah. Let me. Yeah, I see you. Yeah.
yeah,
So you will be presenting both the papers, right?
yeah, I have present.
Yes, sir. Thank you. Good morning, Dr. Murugan. Thanks for joining.
Hey, good morning, Karthik. Am I audible?
Uh, yes, Dr. Murugan. Yes.
Thank you.
We will start session three in 5 minutes. It will be 10 Central or 11 Eastern time.
Yeah, sure.
Good morning, Anirudh. Okay. Dr. Murugan, I think you and Nasruddin are representing two papers today. We'll wait for a few minutes. If no one joins, we'll start with 225 and 265.
Yeah, sure. No issues. Thank you.
Okay, let's give it 1 minute or two because everyone is moving from the other Zoom where the keynote was there to this Zoom.
Okay, fine.
Good morning, everyone. Let's give it 2 more minutes. Let's wait for a few others to join the call, and we can start session three. Good morning, everyone. Welcome to session three of the International Symposium on Digital Forensics and Security. My name is Karthik, and I'll be serving as a session chair. This session brings together a diverse set of contributions spanning from AI, data, AI-driven security, malware detection, database systems, smart city surveillance, digital forensic applications. We have several exciting papers lined up. Each presenter will have approximately 10 minutes, followed by a brief Q&A. I will indicate at the 8-minute mark so presenters can wrap up accordingly. Uh, I kindly request all presenters stay within the allocated time so we can keep the session scheduled. Um, uh, so we can start the session if everyone has joined. Let me check if uh, let me check the list attendance participation list. Uh, let's start with paper ID 19, AI-powered Android immune system and hybrid static and schematic model for malware neutralization. Is Mr. Mohammed Fozal over here? We will move to the next one. We'll come back to paper ID 19 when the participant is available on the call. The second paper is paper ID 19, SQL versus NoSQL Comparative Analysis of Database Management Systems for Scalability and Performance by Mr. Ravi and Mr. Vishwa. Uh, is Mr. Ravi or Vishwa on the call? Anjana, session 2 has a different Zoom ID. Um, so Ravi is not on the call, I guess. Let's move to the next paper, and we can come back to we can come back to the paper one and paper two later. Paper ID 225 research study on AI-driven weapon and violation Violence Detection in Smart Cities by Dr. Murugan and Mr. Nasruddin. Uh, Please start your presentation.
Yeah. uh, So my slide is visible?
Yes.
Yeah, thank you, sir. So good morning once again. So myself, Dr. Nasruddin Ahmad from College of IT, United Arab Emirates University. So today I'm going to be present. Our paper title is Research Study on AI-Driven Weapon and Violence Detection in Smart Cities. I'm very pleased to be present my paper on behalf of my teammates. So thank you once again. Yeah, once again. So these are my presentation outline today. So the introduction. So nowadays that due to the urban cities, the wherever the people gathering, for example, malls and streets and all other gathering areas, we have to provide the safety for the people. Am I right? So for example, if anything happen, any crisis happen, how to secure the people due to that crisis? So obviously every places we have to install the CCTV cameras. Am I right? So what are the limitation of the traditional system in the sense every time people that the human supervision manage all the things. So due to this human, so they maybe face the fatigue or delay responses if any incident happen. So we have to overcome those issues. Nowadays, the emerging technologies like AI and computer vision, we have to integrate this kind of that urban security. For example, if any crisis happen, we have to detect that any weapon immediately, and we have to alert that people. Not only in that, in that for the particular incident, we have to provide that people safety also. So that is that our ultimate motto. So wherever it applicable means smart city integration. For example, nowadays each and every countries they have to from small urban to rural, they have to provide the smart city scheme. So in the smart city scheme, we have to ensure the public safety, and in case they have to any incident happen, we have to create the awareness, and if any incident happen, we have to reduce the response time comparatively that traditional system. So that is our ultimate aim. So what are the problem statements so far? For example, the human error, because we have the traditional system that all the relies that systems relies on the human method. So they, in case if I'm that CCTV monitoring management system person, so I have in case any incident happen, so I have to check the all the things from scratch to all the incident happen. So it take delay. So that is the one problem. And concealed weapons, for example, any small or partially concealed weapons, it's very difficult to we have to find that in the low light or other crowded environment. And the next, fragmented system. So why we have to focus fragmented system means because in the weapon in the sense it's not like only one weapon, so it may be different. So in that time, how do we have to segregate that one? So that is the one problem in that one. And how to alert after that incident happened, how to alert the rest of the people. So that is the problem. So we have to consider all these problem statements, and we have to move on that our proposed suggested system. So these are the bottleneck of traditional surveillance. Obviously, we have to one that we have to go to that the CCTV that room, and all the people's running here and there, and if any incident happened, they have to check from where that persons came and how the incident happened. All the recordings they have to take, and meantime that victim is already have dead or some whatever. So how to avoid this traditional manual monitoring, how to incorporate this AI to overcome these issues. So from this AI, we have to integrate the deep learning and computer vision. So we have to continuous 24/7 processing and alert immediately, so we can secure the rest of the people. So that is our motto. From this, our objective is we have to take in that many papers from the reputed journals and conferences, and we have to detect one. Our motto is they have taken that weapon detection and violent recognition, and we have to identify the research gaps from those appropriate papers. For example, how to that requires the further development, how to increase that accuracy, scalability, what are the system integration with it done, all the things. Then we have to include that our proposed smarter system. So that is our objective. So I move to the next slide. So this is the anatomy of AI video analytics. For example, in the traditional one, this is a That is standard, am I right? So we can't after incident happened, we have to recording the recording scheme, recording data they taken, and we have to go to from that we have to analyze one by one, scene by scene. So now we have to taken from that live record CCTV feeds. From that video, we have to go to the deep learning extraction. For example, identify the object or whatever the actions happen. Then we have to go to the confidence of that score, which means how to storing that minimize false positives and other things, and after that we have to alert that one. For example, if that particular where is that geolocation happens, so immediately we have to alert that things, so it will helpful for the law enforcement people. So that is the our motto. And these are the weapon detection related works. So we have to taken some plenty of papers, but we have to given sort in our your kind notice. So there are a lot of people already, they have implemented their techniques. They got it some results relevantly. So for example, the first authors they taken from the real-time data sets, they applied the faster RCN and FPN. They got it 94% accuracy and 90 ms per frame. So similarly, each and every one, they have own techniques and they get it results. So then how we have to, how our method is unique in the sense, we have to use it that AI things. For example, in this one, see, they are used it as YOLO variants and the accuracy, they get good accuracy. But what is the key limitation in the sense? Accuracy drop when we go to that low lighting source. So we have to avoid this kind of low light environments and other things we have to improve. So why we have to move YOLO in the sense? So YOLO, it's worked for the detection. So that's why, and the CNN for the classification, the weapon detection. So that's why we have implement this one. And violence detection. So the violence detection, they have taken from the data sets from that occupied data sets and URFall data sets. They have to take the real time some CNN and LSTM. There are many people, they have already they implemented the techniques and they got the results appropriately. So we have to give kindly bring notice few things into you. And how our things is different in the sense, for example, we have to finding the isolated objects and the particular moment, and how to tracking the people from on identify the behavior. For example, they have to punching, they have to pushing. So we have to the abnormal behavior we have to detection with help of this AI computer vision. And there are many people, they have the same thing, they have get it good accuracy with help of this YOLO or the different the suggested approaches. But till now they have problem in the sense efficient enough localized edge devices and distributed that edge nodes and edge servers. Sorry, that is the problem. Sorry. And yeah, so our proposed system overview, we have to detect the real-time weapon and violent activity, and also we have to automated alert that people, and we have to properly store that investigation, I mean that particular evidence, and it will helpful for the law enforcement scheme. So that is our ultimate aim. So these are the system
We,
architecture.
we are at
Yeah,
the 8 minute mark.
yeah. I just move on faster. So the next that this is the things. So obviously first we have to take that from the CCTV the incident. Then we have to go to the edge computing. We have to we have classified two things: weapon and violence. That then we have to alert that and reporting and to the law enforcement scheme. So our aim is we have to reduce the latency and enhance the scalability with help of this edge computing layer. This concurrent detection at the edge, we have to take in the two streamlines. The one is YOLO pipeline and CNN LSTM. So YOLO obviously we use it for the detecting and CNN used it for the classification. Then finally we have to get it the output. From this one weapon detection model from the CCTV camera, we have to extract the frames and pre-processing with help of YOLO. Then classification, the type and size, for example, tracking the weapon, because we have to take in the two kind of weapon. For example, and not only in a gun, we have to use it the gun and rifle, and in the from the gun only there are different types of shotgun and other things. So that is the we have to our classify. So the with help of CNN, and similarly the violence detection model. In the previous slide, I already told that taken the data sets from the Docufied data sets and URFall data sets, and we have to use it this CNN and LSTM, the tracking via the behavior of that violence, where the people gathering, and with then immediately alert the system. So here violence in the sense abnormal in the sense they may be fighting or pushing, running, whatever. We have to classify all the things. So that is that thing. And these are the system workflow. And Yeah, advantage of our proposed system is we have to identify the very fastly, and with the help of this edge computing, we have to reduce that latency and improve the accuracy. Okay. And what still now they have challenges is there. For example, improve the tracking accuracy in the low light environments, and expanding in the future, expanding the range of detect weapon types. For example, now we focus on only the knives and gun. In future, we have to a variety of the things, and reduce the false positive and negatives to improve the reliability, and finally accurate the analysis in the high density crowd situations. And again, the conclusion, with the help of this AI computer vision in the smart cities, it helpful for the enhance the public safety. And we have to that propose the weapon that violence detection in single framework, and improve the threat identification, and also alert the people with the help of this emerging technologies. And yeah, I hope so.
Yeah.
Yeah, and we have thanked to our colleagues sponsored this these things, and thank you to all the people. So these are the references, all are the
Sure.
recent papers, and thank you once again.
Yep.
Yeah,
Thank you for the presentation. We are
yeah,
open for the floor for the questions if anyone has.
yeah, yeah.
Uh, Dr. Nasiruddin, the next paper is also yours only, right?
Yes, sir. Yes, sir.
Yeah, please go ahead with it.
Yeah, if anybody have questions, sir, or otherwise, shall I move to the next one, sir?
Yeah, anyone has questions?
Okay, sir. Then shall I move to
Yeah.
next one, sir?
Yes, yes, please.
Yeah, thank you, sir. So I hope so my screen is visible.
Yes, your screen is visible and audible.
Yeah.
Yes.
Yeah, thank you once again. And that our paper title is the enhancing detection of bloodstain patterns and footprint impression using deep learning. So again, I'm very happy to be present this paper on behalf of my team. So and directly go to this one. So due to the time constraints, these are my outline. So our aim is the crime scene investigation. So it's a very important because, for example, if any incident happen, definitely the crime that forensic people will come and recover all that evidence and collectings. In this one, definitely they have the manipulation came, that human manipulated and contaminated that crimes and all the things happen. So our focus is how to secure that all the evidences, especially we focused on BPA, which means bloodstain pattern analysis, and foot fears. So these two things we focus. So from this one, we have to collect that incident, that particular incident. From that incident, we have to we have to secure that all the things, and finally we have to provide some accuracy. So what are the core challenges so far in the sense? So we have to rely this, especially the blood pattern and footprint. So we are visual inspection and subject interpretation. So introducing variability, bias, and error and things. So that it's a technically it's may confuse, and I'm in the upcoming slide it will be easy. So for example, see the limit of manual interpretation. For example, few things may be visible and few things we cannot visible. For example, bloodstain pattern analysis. In the bloodstain, the name itself it's very easy, but the categories is very the variety. Because for example, if you go to one person shot, the zero and the shot in very short range, that scattering of that blood is different. Maybe the shotgun, if the smart shotgun means that blood pattern is different. If the knife stabbing, that blood scatter is different. So that is the one category. So our motto is how to the blood scatter only we have to analyze this. So what kind of crimes happen we have to analyze. And similarly the footprint. So footprint in the name itself easy, but what kind of footprint? For example, it's what a kind of age, the people, either man or male or female, everything we have two things. And finally we have to with the help of this one we have to secure and fragmented analysis. One is blood, another one is footprint. So other things. And then the next is, this is the objectives. So our technology, so unified deep learning framework. So with the help of this UDL, we have to we have to focus on multiple evidence types. Why multiple evidence type means the traditional one focus on one evidence type. So our proposal is multiple evidence types. So one is blood, another one is footprint. So VAT. So VAT based. This is for the blood pattern analysis, which means classify the blood stains. And another one is ResNet. So under that apply CNN. So it's the classification of the footwear categories. And so bloodstain pattern analysis. The so far the many people they started their own suggested methods, and they have to get it the appropriate results. But till now the limitation is only the very less data sets. There is no go to the real time data sets, and only focus on single the single evidences. So that is the problem in the sense. Similarly, the footprint also, they have to detect only the footprint. So they're not focused on whether age of the particular person, what is that, either male or female. There are a lot of problem in that limitation in the footprint analysis. So our motto is we have to focus on multi-evidence instead of single evidences. Why? In the sense, because we focus on blood and footprint, and then next data sets, because we not go to the lab data, because we go to the real-time data, and environmental variability, because the lighting and textures, other things, some issues will come. So we have to improve that reliability, and with the help of this AI technology, we have to improve that improve the variability and identify the research gap. So that is the one thing. And these are that current landscape. For example, I already told the Bloodstein categories. So with the help of this one, we have to classify it, and highly accurate but strictly single purpose. The footprint, in the sense, with the help of YOLO, we have to classify it, because the male or female and other things. So once again, I repeated, this current is the current and propose the classification. See, evidence is the main important, both whatever, because after evidence only we have to find the culprit. So, but in the classical one is focused on single category. So our proposed method is multi-category, so bloodstain and food waste. And for the final, the traditional one is a deterministics, and we have to get the probabilistic output. So from this probability score, it will help to that forensic scheme and that crime investigation teams. It will help to find the victim as soon as possible. And so we have to take it from the bloodstain data sets. Similarly, footwear data sets. From this one, we have to pre-processing. So pre-processing, nothing but we have to resizing the particular images, normalizing and other things, the background removal, because with the help of this technology, because so finally we have to go to the step one. Obviously, the forensic scheme, they came and take the capture of the particular crime scene. Then we go to the pre-process, and we have to extract the two categories. One is bloodstain, another one is footprint. So bloodstain, we have to use the VIT base, and that footprint for the ResNet. So that finally get it that unified report, and we have to send to that this one. And I already told that the very introduction slide, because that for example, blood pattern is different categories there. Am I right? So with the help of this vision transformer, we have to analyze that one classified and what kind of output classes will come. For example, drip, impact, cast off, transfer, expirated. So this is one thing. And then model 2, this is for the ResNet under the CNN, because classified that the gender classification and what kind of what kind of pressure they will put it in this one. So from this pressure, we have to analyze what kind of happened. For example, if that culprit came and just strangled the victim, from that moment, the heat of the moment, that the victim and the culprit, they have to pressure the more the footprint. From this one, we can easily identify it. So that is the one thing. And so experimental setup, we have taken this hardware and program and deployment. So we have taken from this bloodstain images, footprint images from this data sets. From we have to split as a 17-15-15 ratio for the training, validation, and testing. And these are the 5 categories of bloodstain. We already told the drip one, and the impact, cast off, transfer, expirator. This is nothing that one. After incident happened, how the blood will spatter. From that one, we have to collect. From this method, we have to analyze what kind of crime happened. So it's really easy to that crime scene people, so investigation people. And from this one, we have got it. The result is 94.3%, our suggested method overall. And similar, these are our results. Samples I put it and bring kind notice to you. The bloodstain gunshot and the vertical drip pattern. These are the bloodstain fine droplets pattern and transverse swipe. And then this is that the footprint. So what kind of gender classification, how much the height, and what the size and other things we have to analyze this. And we got it the results from the 91.6% overall accuracy. So these are that our results: footprint, male adolescent and female adolescents. I already told that what kind of shoe size and height and age, the sex, and these are the categories we have to split up. So this is the suggested methods. Similarly, male child, the female child. So what is the age and height, shoe sizing, and sex? All the things we have to classify. So this is our suggested methods.
8 minutes remain.
Yeah. Thank you to remember. So discussion. So fine for that one. So we have to bloodstain challenges, in the sense I already told. There are some, that low light environment, that is very problem. Similarly, footprint also, that age group, how to, clustering, that is also problem. These are the discussions. So, yeah, I directly go to. So from that one, we have to contribute with the help of this robust deep learning technology. We have to classify the bloodstain and footwear from the public available data sets. So similarly, so till now the limitation is, I already told, the low light environment variability. So we have idea in the further researches. We have to go to the real life data sets and improve the robustness, and for it's helpful for the forensics deployment. And these are the references we have taken from the repeated journals and conferences. And again, I thank to our college to sponsor this one. And thank you our team also. And thank you, sir.
Thank you for your presentation.
Yeah.
We are now open for the floor for questions. Does anyone have questions for Dr. Nasruddin and Dr. Murugan?
Yeah.
Yeah. Thank you, Nasruddin and Dr. Murugan, for your time.
Yeah,
Uh,
thank you, sir. And thank you.
I'll move to the next. I'll move to the next presentation and come back to the paper ID 19 and 56. We'll go to the next paper ID, which is 296. Evidence quality telemetry for cloud incident response, detecting gaps, drift, and integrity failures in large-scale observability pipelines. Mr. Chalapati, Konneni, Mr. Sanjay, anyone on the call?
I'm there. Sanjay, you're there in the call?
Yeah, Chalapati, you can start it.
Can I come back once my partner is here?
Sure. Okay. We'll go to the next one.
Yeah.
Um, paper ID 396. Blood trace and blood test weight drop become decision. Mr. Ranganathan,
Yeah,
are you
I'm
on the
here.
call?
Yeah.
Yeah. If the floor is yours, please,
Okay.
please present.
Uh,
You can start sharing your screen.
yeah, just give me a second. Sorry.
Sure.
Is my screen visible?
Yes, your screen is visible.
Yeah. So good morning to all. My name is Dharnidharan, and I'm a graduate student at University of Winnipeg, and I'm here to present our project, Blood Trace, where drops become decision. So this is the outline of what we are going to go through. We'll be going through just an introduction and a prior work and its limitation and framework and our framework and the result validations which we got and why this interpretability matters in forensics and the limitations we have which and how we can resolve it with a final conclusion. So, like bloodstain pattern analysis helps reconstruct events from the blood spatter patterns. And right now, this analysis is manual, subjective, and is time consuming. Our approach is a binary classification for now. So it just classifies between gunshot and blunt impacts. So gunshots gives creates this fine mist with many tiny droplets, and blunt impacts produces a larger droplets that cluster near the sources. Uh, so this is the kind of the basic idea which we had when we started this, and till now this is what we used as a base idea to work it out. And the existing automation methods work really good in a lab setting, and but where they fall apart when the image conditions or a background changes a bit, and that is what we are trying to address in our project. So here you can see the difference. On the left hand side, you can see a gunshot spatter pattern, and on the right hand side, you can see two impacts. One is a blunt force, and next another one is a passive drop. And there are other things in this bloodstain pattern analysis, but right now we just started with the binary classification. So these visuals gives difference in sizes, counts, distributions, which are exactly what our system tries to learn and classify. So before we get into our approach, let me just quickly cover what's been done before. This is like the baseline method which we used, where it uses a grayscale thresholding and identifies the blood regions. They fit ellipses to each stains and extract the geometric features. And they use random forest or XGBoost. and these methods achieve around 93 to 95% of accuracy on their test sets. This worked really well, but the problem was that the test data and the training data all were a lab setting, which were high resolution images. And when the background changed or lighting condition changed a bit, the accuracy drops nearly to 50 to 60%. So these methods don't generalize well beyond the lab. So this is our framework. We start with an input image and run it through segmentation. We have a dual path segmentation, which we'll cover in upcoming slide. From those segmented regions, we extract features which we use into a cat boost classifier. It's a gradient boosting algorithm that really works well with tabular data. And we also calibrate the outputs so that using isotonic regression and beta calibration. So when the model is like 80% confident, it is actually 80% confident and without anything. And finally, gives the output with the prediction and along with the calibrated score. So this is the segmentation strat. In this step, the goal is to isolate only the blood region from the input image, so we can analyze the stains accurately. So we use two segmentation paths. The main segmentation uses a strict HSV color thresholds, which detects clear blood stain and tiny droplets. If the results look uncertain for this, for example, in the end, if the confidence is low, or if the coverage is sparse, or if there is very few stains detected, a contingency path will be used, which has a more relaxed threshold and it recovers fine micro droplets. Basically, this whole idea of the segmentation process is like having a 2 point of views. One looks at the whole picture, and one really focuses only on the micro droplets, which is like the tiniest one, which helps you to identify the difference between the gunshot and the impact. So this actually improves the detection for subtle spatters. And this is and the features we extract are uh, across the several categories and coverage and size features that measure total blood area and count individual stains, and spatial distribution features show whether stains are widely dispersed or tightly clustered, and shape and orientation features captures things like how circular versus elongated stains are, whether they follow directional trends. The shape and orientation features basically resemble the baseline model, the geometric features. And we also add intensity and color features, so which uses grayscale levels and red dominance, which gives us an extra information. And together all these represents both physical characteristics and how the blood was dispersed, and visual characteristics where what it looks like in an image. So let's move to our data set and results. So we worked with the 905 images in total. We started with around 114 original high resolution images, and we augmented them into rotation flips and contrast adjustments to make the model more robust. So the original images were captured on a white poster board under a controlled condition on high resolution images, which were used in the baseline model. But we also included some external validation images on non-white backgrounds with varied lighting and cam angles, basically the augmentation we used. And so this was important for us to test generalization, and we used a 80-20 split, stratified 80-20 split, and made sure that the augmented version of the same image stayed in the same split. So this allows us there's no leakage. And for the pre-processing, we resized every image to a max dimension of 1000 pixels, so that it's computationally efficient. And for that, we got on our held out test set, we achieved a accuracy of 95.6. And for gunshot and impact patterns, the precision and recall shows that we are getting good performance on both classes, and in mostly impact gets more. And the ROC and AUC is really close to perfect, and overall these numbers shows that the model can predict between the two pattern types really well. So this is the external validation. The main thing we wanted to do was that the baseline failed if if lighting condition or a background changes a bit. So we wanted to make sure the generalization goes to some extent. So this shows. So we tested both our approach and the baseline method on an external validation image that weren't seen during the training or anything. So this represents more realistic variations in image conditions. So the baseline grayscale thresholding performed well on the controlled image, as I told, and it went nearly 50 to 60% on an external image. Our approach maintained approximately 90 accuracy overall, like on the gunshot or impact. Impact, it gave a pretty good result, but for the gunshot, it was nearly 90% accuracy. But I want to be clear about what this means is that improvement, this improvement demonstrates that our method generalizes to some extent beyond the lab. It works maybe on cardboard or fabric or a glass or conditions that are messier than the training data, but still is somewhat controlled. Well, a real because a real crime scene will be even more complex, and we'll be having there can be a lot of patterns here, patterned surfaces, aged blood or blood turned brown, or environmental contamination, and a lot of stuff is to be included. We haven't tested on that level of messiness yet, and I cannot guarantee the performance in those conditions. But this external validation helps us to show that we are moving in the right direction.
8 minute
So
mark
the
remain.
features, sorry.
Eight
Yeah,
minute
sure.
mark
Okay.
remain.
Yeah, I got it. Thanks. So the features which actually matter, the cat boost model which we used identified the blood coverage as the most important features, and the other important features included stain count, spatial dispersion metrics like R50 and R90, which shows the spread out pattern, and the clustering density captures the spacing between stains. The good thing about these features is that this important features used, which will help the basically helps us to establish that interpretability of our approach is doable in a way. So why we did feature based instead of deep learning is that in forensics the interpretability is important as the accuracy. The features we used are transparent and can be validated. Deep learning gives the highest accuracy, but our approach is demonstration that interpretable methods can achieve competitive performance with transparency. So basically, each decision made can be tracked back to the observable characteristics. So this helps us show that it's a viable direction, and we thought it's worth exploring further, and we might explore it further. So I want to talk about the limitations that we have. Like I told before, it might generalize to some extent, but real crimes in data are more complex. And the system right now only handles a binary classification between gunshot and impact, and there are a lot of other stuffs we need to do, like cast off, arterial spray or drip patterns and other stuff. And having a fix now, right now the thresholds are fixed, which has worked out well for this instance. But in the future we should have an adaptive threshold which is more better than a fixed threshold. And for the future steps, we need user studies to understand what features are valuable. Like right now we didn't have a clear idea, so we implemented a lot of features. We There may be some of the features among them which might not be actually useful, or it's just an extra features. So we need user studies to understand what features are valuable and how this can be integrated into existing process, and extending their pattern types and in long term process. And also get lot of data sets, which is really hard to get an actual crime scene data set. And in long term process we envision a hybrid approach where the features can be interpreted, and segmentation can be done using deep learning, which would give a better segmentation than what we have now.
Yeah, we,
So
we are we are out of time. Can you wrap it up quickly?
oh yeah. So yeah, to wrap up of all what I've covered, I just wanted to say that the main idea of the work is not to say it's the best approach to do what and stuff, but to demonstrate that the interpretable machine learning can achieve a competitive performance and maintaining transparency. And this can be a good consideration for the forensics application, where you can need to explain your reasonings. So our codes are available on the GitHub, and thank you for the opportunity
Yeah.
and all.
Thank you for the presentation. We'll open the floor for a minute for questions. Uh, th- Anyone in the audience have questions? Thank you, sir, for your presentation.
Thank you.
We'll move on to the next presentation. Mr. Chalapati, you can start, and Sanjay, you can start your presentation.
Yeah. Let me share my screen. able to see the presentation?
Yes. You
Okay.
have 10 minutes total. I'll remind you at the 8 mark.
Okay. Sure. Sure, Karthik. Yeah.
Sir,
I'm
you
thankful.
have the slides in a presenter mode. Can you switch to the normal mode? It shows the comments in the presenter mode.
It shows the comments also.
Yeah.
Um, okay, what? Now also you see the comments.
Still shows.
Okay. Can you share, Sanjay? I can walk through. I don't know why it's happening.
Is it better here?
Let me stop sharing. Okay, can you share it now?
I think I'm already sharing.
Can't see the screen.
It looks better. Please go ahead.
Okay. Yeah. So one second. Okay, so today we are talking about evidence quality telemetric for cloud incident response, right? In the recent our current cloud systems, we capture a lot of data set with high velocity, and it relies on high velocity telemetry streams such as logs, metrics, traces, events, and we with our experience we generally go with like quality later, and capture the data fast and then get the quality later. With that, like observability and the reliability of the data set goes a little bit off. And then what we thought is like, why can't we introduce quality metrics into the pipeline itself, inline pipeline itself. And then we came up with this approach of like including the quality metrics in the pipeline itself, right? uh, First we'll go with introduction. uh, Cloud system, like as I said, cloud system rely on high velocity telemetry, and observability drives in automated incident response, right? If we have good observability and good quality and automation, you can respond to the instance quickly. If not, it would take time for triage, all the stuff, and data recovery, all the things, right? Based on what I know we have learned from industry experts, more than one third of applications rely on post quality or post observability incident responses rather than like inline quality metrics. And these decisions are responsive decisions are often made with some incomplete data in case of any issues that happen. And data trustworthiness is rarely guaranteed in such kind of scenarios where instance happens. And if the quality and telemetry quality is captured after the data is logged in high velocity telemetry applications, because the data would be coming faster, and there will be variety of data sets. Once the data is gone, stream is gone, the data quality is gone for any of the records that are that had issues with the quality, right? And our work begins premise with telemetry must treated as evidence. So therefore, the quality assurance must be embedded into the pipeline itself, instead of like putting the quality later into the pipeline once the data is addressed, right? The problem statement is observability assures the trusted data set. The core problem is that observability systems operate under trust first assumption. Like we assume that data is coming into the streams is accurate or correct, or the source systems work, or the applications work as expected. But that is not true in reality in most of the times, right? As I was telling in my opening statement, the quality checks are post processing in most of the applications that we design. And then like, and when the quality checks are post uh, processing, then the drift anomaly, and detecting the data issues, all those things would be once the data is captured. And mttr mean time to respond for the instance is also higher, right? So we want to tackle this problem and see how we can embed the quality into the inline pipeline itself, right? And the objective is, like as I was telling, the embed quality by design architecture, and enforce integrity and completeness into the inline pipeline itself, and detect the drift real time while the data is flowing, and correct the data if possible in the on the fly rather than like post incident happens, right? Like the last point is like, remediate automate the remediation once once the issue is detected inline. Try to remediate the data itself in the um, in the remediation workflow. Sanjay, you can go to next slide. Sorry, I forgot that, like, I'm not sharing the screen. So can you go to the next slide, slide 5? Architecture overview. Like we had a 5-layer pipeline design, and each layer has its own unique responsibilities. We're going to talk in the subsequent slides what are those 5 layers that we consider for our experimentation, and those are like, inline validation checkpoints, and then like distributed quality enforcement. Like the quality enforcement also, like, considering the region and the scalability of the application in case of, like, to reduce the latency. So we considered all these things and come up with the architecture. Unlike traditional pipelines, the quality validation is not a separate downstream pipeline in our experiment. Like, this one is like included in the pipeline itself, right? The first layer is data collection layer, and the collection layer represents the first line of quality enforcement. It operates on volatile data sets, distributed cloud environments, and this layer collects the data, and then preserves the signals in case of overload conditions, right? And the collection layer is also region aware. Like, we enabled the localizations for fault isolation, and and also, like, we embedded prioritization policies early in the pipeline so that, like, the downstream validation goes smooth, right? And yeah, stress aware. Like, the other point is stress aware data preservation. And the next layer is validation layer. The validation layer comes in the pipeline itself, like I was telling, right? And here in this layer, we
Eight
detect
minute
the
reminder. Just a reminder,
uh,
8 minutes.
the next layer is cryptographic integrity, and here we isolate the data that has issues, the detected part of the pipeline. And then drift detection, we dynamically calculate the drift based on the historical data set and data that is coming in the real time. And the latency here is like, 5 sub-second latency. And automate remediation, as I was telling, remediate the pipeline data issues that are identified in the highly critical fields, and then pass it to the layer that is captures the data set, right? And now I'll hand over to Sanjay. He'll talk about the implementation.
We have implemented this framework in a multi-region Kubernetes deployment spanning between like multiple regions. The system processes approximately like 15 terabytes of data from hundreds of virtual machines. Apache Flink is used for stateful stream processing, while a Kafka is ensuring the partition event transport. We use OpenTelemetry and Fluent D for to handling the ingestion data. The overall large-scale setup allows us to simulate the cloud workflow environments and failure modes. Performance overhead, like, if we only see the base ingestion and the throughput, the baseline latency was around 50 milliseconds for the event to store. But after adding the validation layer, the latency was around 95 milliseconds, which was 90% overhead. We have 45 milliseconds or 90% overhead. We saw a minimal distortion in the throughput, which is around 10%. Resource utilization, each individual validation pod in Kubernetes, we configured like 4 cores, but the average CPU utilization was less. The validation consumes like all these validation pods have 4.2 GB of memory, and we saw a throughput of checkpoint writes around 22,000. We also have tested the horizontal scaling, like especially on scaling from hundreds of resources to thousands of VMs, like where the telemetry is getting provided. Even after tenfold increase, we still see 45% latency only from 95 milliseconds to it went up to 145 milliseconds when we went to like 10x fold. The throughput was still on the same lines from 75K events per second to 70,000 events per second. Moving on to detection metrics, yeah, the overall recall for anomaly detection in the validation layers was 0.983. So it's very highly sensitive model. The precision was low. It was kind of intentional in security-based systems. It is okay to have false positives, but no false negatives. We wanted to keep it more sensitive. Any underlying the trade-off was very intentional, and especially because of the security system.
Could you
Downstream
wrap it
correlations.
up quickly? We are at the
Yeah,
11th minute.
sure. So we have seen how this bad data is impacting on the downstream ML models, but we haven't observed any major downstream impact. Mm, Yeah, I'll go to the practical implications. Establishing telemetry trust boundary. If telemetry is not trustworthy, then the underlying analysis or anything on the root cause analysis or forensic analysis is kind of void. So the current limitation is like 90% latency. We wanted to continue to work on reducing the latency, and the low precision, we want to work on the low precision areas as well. And the overall work is more native AWS Kubernetes approach, which was, that was the primary infrastructure stack we used. We will continue to, the future work is more on smart NIC hashing and using multi-cloud federation to improve the latency and precision. Thank
Thank you,
you.
Sanjay. We'll open the floor for any questions. Yeah. Thanks, Sanjay. Thanks, Shalpati, for your time.
Thank
Thank
you
you
very
so
Uh,
much.
much. Thank
Thank you very
we'll
much.
move to the next one, and then come back to the paper one and paper two. We'll go with paper ID 434, AKURA Adaptive Sinhala Learning for Early Childhood Using Gesture, Voice, Emotion, and Handwriting. Is Mr. Mehiran on the call?
Yes, sir.
Oh, sorry,
Is
Mr. Mehiran. Yeah.
is my screen visible?
Yes, your screen is visible. Yes.
So, good morning, everyone. Today I will present our paper titled Akura Adaptive Learning for Early Childhood Using Gesture, Voice, Emotion, and Handwriting. So, this work focuses on improving early childhood literacy through a multimodal AI-driven learning approach. So, let me begin with the problem overview. Childhood education in Sri Lanka faces several structural and teaching challenges. First, classrooms are often overcrowded, so individual attention is limited. Also, children mainly learn by repeating things, but they don't get much feedback during the process. So, many learning errors remain uncorrected during early stages. Then, there is a limited progress tracking, so, teachers and parents lack visibility into individual learning gaps. These issues accumulate over time. So, studies indicate that a significant percentage of students do not achieve basic literacy levels by early primary education. Now, looking at existing digital solutions, most applications are static. They present content and evaluate final answers, but they do not analyze how the child arrives at the answer. So they fail to capture writing behavior, pronunciation errors, or engagement during learning. Therefore, there is a clear need for system that is adaptive and process aware. So to address this, we propose Akura. Akura is a multimodal mobile learning platform designed for children aged 3 to 6 years. So it integrates multiple learning signals to provide a personalized experience. So unlike traditional systems, Akura focuses on the learning process and it continuously analyzes user interaction in real time. Then, based on this, it adjusts task difficulty, provides immediate feedback, and guides the learner step by step. Also, the system includes emotion aware adaptation. So, it responds to the child's cognitive and emotion state. So, importantly, the system operates fully on device. So, this ensures low latency, offline accessibility, and strong data privacy. Now, let's look at the core components. Um, so first one is handwriting learning. So this module performs real-time stroke level analysis and it evaluates writing path, direction, and stroke order. So instead of only checking the final shape, it analyzes the writing process. Then immediate visual and haptic feedback helps correct errors during writing. And the second one is gesture-based numeracy. So this module uses real-time hand tracking to detect finger-based counting. Geometry-based algorithm interprets the finger state and then the system identifies error patterns and provides corrective feedback. So this supports intuitive and interactive number learning. And the third one is pronunciation module. So this module evaluates spoken Sinhala at both word and phoneme levels. A fine-tuned single speech model detects mispronunciation, then the system provides auditory feedback. So this supports accurate language development. And finally, we have emotion adaptation. Um, so this module detects learners' emotions using facial expression analysis, but to ensure reliability, adoption is triggered only after the consistent detections over time. Then, based on this, the system adjusts difficulty, pacing, or guidance. So this helps maintain an optimal learning state. Now, based on these components, let's look at what makes Akura different. In traditional systems, learning is mostly outcome based, and also most systems use only a single type of interaction. And another limitation is cloud dependency. Now, briefly on implementation. The system is developed using Flutter for cross-platform deployment. So it works across multiple devices, and also we use here MediaPipe for hand tracking, MobileNet for emotion detection, and fine-tuned single speech models. So the system is designed for low-level resource mobile environments. Mm, Moving on to the evaluation results, we conducted component level testing. The results were for the handwriting accuracy, we got 95 and 93.4% for gesture recognition, and pronunciation error rate was 8.1%, and emotion classification got 92.5% accuracy. Also, we evaluated the system with preschool children by visiting preschools. Uh, so for the future work, we plan to expand datasets to improve model robustness. Then we aim to enhance personalization mechanisms, and also we plan to support broader classroom integration. And so this includes scaling to more devices and environments. So, in conclusion, Akura presents a novel multimodal framework for early childhood Sinhala education. So, this enables real-time personalization learning in resource constrained environments. And here to the end of the session, and thank you for listening.
Thank you, Mehiran. Um, the floor is open for questions. Anyone has any question for Mehiran? So, Mehiran, I have a question for you. Is this mainly focused on childhood education or even for adults?
Childhood education, sir, specifically for
Childhood.
yeah.
Yeah, thank you. Any questions for Mihiran? Thank you for your time. We'll move to the next paper, which is paper ID. I'll go back to the first paper, which is paper ID 19, AI-powered auto Android immune system, a hybrid static and schematic model for malware neutralization by Mr. Mohammad Fozal Rabi. Are you available on the call? We'll move to the next paper, which is paper ID 56, SQL versus NoSQL comparative analysis of database management systems for scalable and performance, by Mr. Ravi and Mr. Vishwa.
Hi, hi all. Just let me quickly share my screen.
Sure, sir.
Let me know if you see my screen. Is it visible?
Yes, it's visible, clear.
Oh, okay, thank you. Yeah, good morning all. Good afternoon wherever you are. So I'm Ravi and my co-author Vishwa. So I'm going to present this on his behalf as well. So this paper is regarding SQL versus NoSQL comparative analysis of database management systems for scalability and performance. So this is for DF, and what is the study matters is choosing a database for scalable web applications remains difficult because performance, scalability, and resource efficiency pull in different directions. So SQL systems favor strong consistency and fast structured reads, while NoSQL like MongoDB systems favor schema flexibility and faster bulk writes. So the paper argues that standardized, reproducible benchmarking is needed. So database selection is driven by evidence rather than anecdote. So like how under the MERN stack conditions, which database performs better for connection latency, reads, writes, throughput, storage, and resource usage. So we have like this repeatable workflow where the standardized MERN benchmark with Docker and Kubernetes or measured outcomes like latency percentiles, throughput, storage, insert or fetch efficiency. So evidence-based trade-offs. So read heavy versus write heavy workload guidance and practical value. So methodology intended for both academic and real-world adoption. So the study explicitly positions MySQL as stronger for reads and MongoDB as stronger for bulk writes when tested under control conditions. So this is the workflow that we try to do, that conceptual study on SQL versus NoSQL data partitioning workload management. So we started with startup MERN application. So from there, we done the configuration of databases MySQL and MongoDB, and which database run my SQL workloads or run MongoDB workloads, and collect the performance metrics, the latency and throughput storage. So the software stack is like front end will be React, back end was Node.js plus Express, databases are MySQL or MongoDB, and desktop plus Kubernetes Docker, and testing Thunder client. So the measured performance dimensions are as stated earlier: latency, throughput, write efficiency, read efficiency, and system footprint. So these are the dimensions that we use: P50, 95, 99, and transactions per second for throughput, and bulk insert total and per record latency for write efficiency, and fetch latency, total and per record efficiency system, and storage plus CPU memory consumption as a footprint. So Docker desktop dashboard. So the paper reports like light overall utilization, 1.1% of 8 CPUs and about 153 MB memory, indicating ample headroom for benchmarking. So API validation before a deployment. So a GET request to benchmark latency return HTTP 200 the success okay after 7.09 and reported latency statistics for 50 connection attempts. So experimental setup pilots. Backend services were containerized with Docker desktop and orchestrated using Kubernetes. So test environment was designed for continuous deployment and repeatable benchmarking under the same conditions. The host machine was Intel Core i9 14900K, 64 GB DDR5 RAM, and 2 TB NVMe SSD, NVIDIA RTX 4080 GPU, and Ubuntu 22.04 LTS. So, two visible runtime components, Express backend on port 3033 and local minikube Kubernetes cluster. So, the connection latencies as shown in the figure, the connection latency MySQL versus MongoDB on the latency on the y-axis. So MySQL interpretation was MySQL shows near immediate connection times 0 to 3 milliseconds, whereas MongoDB ranges about 280 to 495 milliseconds. The paper therefore positions MySQL as better for applications that frequently open and close connections. And if you see the figure 6, fetch 1000 records. This is MongoDB and the MySQL on the left side, which is y-axis. So if you see the MySQL lead was the read result is 32 milliseconds to fetch 1000 records in MySQL versus 570 milliseconds in MongoDB. The takeaway is read heavy, structured, low latency applications are the strongest fit for MySQL in this benchmark. So the insert 1000 records. So MongoDB completes the bulk insert in 439 milliseconds versus 3013 milliseconds for MySQL. That is more than 6 times faster in this write heavy task. And the figure 7 of elapsed time throughput. So both systems executed a similar number of operations, but MySQL delivered greater than 1000 TPS with less than 200 milliseconds elapsed time, while MongoDB fell below 100 TPS and required around 2000 milliseconds. So the trade-off summary is MongoDB is a stronger choice when rapid bulk ingestion matters most. MySQL is a stronger choice when sustained transactional speed and throughput matter most. So this deck preserves the paper's central conclusion. Workload profile should determine database selection. So as shown in the latency statistics, the MySQL produced far better throughput for 1000 TPS and far less elapsed time. So on the other hand, MongoDB consumed around 2000 milliseconds or even more as elapsed time, and its throughput was reduced to less than 100 TPS. This clearly indicates that MySQL is much more suitable for structured transactional workloads in terms of speed and efficiency. As it can be seen here, the average latency is 1.12 milliseconds for MySQL, whereas versus 92.76 milliseconds for MongoDB. So 6 milliseconds versus 133 milliseconds. And MySQL is a latency winner. So these are the distill for the presentation in metric, MySQL and MongoDB. The connection latencies, how an insert for 1000 records, fetch 1000 records, insert efficiency and fetch efficiency. So bottom line is
You're
read
at
heavy
the
workloads.
8 minute mark. Just a reminder.
Sure. Yeah, sure. Thank you. So read heavy workloads, low latency matters, transactional structure matters, then we have to choose in general by MySQL. And when bulk writes dominate, schema flexibility is important. High volume ingestion is the priority. Then we'll go to MongoDB. So as the statistics shown above, so the statistics of MySQL is almost 3 milliseconds for connection latency, and MongoDB is 280 to 495. So the conclusion is does not claim a universal winner. What we want to do is instead it shows a clear workload dependent trade-off. So MySQL best for read intensive, low latency transactional applications, and MongoDB is for best for write intensive, schema flexible applications. So the presentation, this takeaway is select by workload, not by height. Reads and TPS favor MySQL, and bulk write ingestion and schema flexibility favors MongoDB. So yeah, this is one. So we are trying to the tools such as Apache, JMeter, and Grafana for richer performance monitoring. And we also evaluate more workload patterns. Distributed cloud deployment, hybrid database schemas also can be uh, uh, do that for future scope, and explore machine learning assistant dynamic tuning for smarter database selection as well for future scopes. Yeah, thank you. Anyone has any questions?
Thank you for your presentation, Ravi. Does anyone have questions for Ravi? Thank you, Ravi, for your time.
Thank you. Thank you.
Uh, we'll go back to paper ID 19, AI-powered Android immune system, a hybrid static and schematic model for malware neutralization. Mr. Mohammed Fozer Rabi, are you on the Zoom meeting? Hello, Chair. If you are on the call, we have we have all the papers presented except paper ID 19. We'll wait for a few more minutes for it, and then we can conclude the session. We'll give a paper ID 19 by Mr. Mohammed Fozal couple more minutes. We have all the rest of the paper IDs presented. Paper ID 56, 225, 265, 296, 396, and 434 have been presented. Thank you all. We'll wait for a few more minutes and then we can conclude the session. This brings us into session three. We had a great, strong and set of presentations covering digital forensics and crime, cloud telemetry, intelligence systems, reflecting the evolving landscape of cybersecurity and data-driven analysis. I would like to thank all the participants for their excellent contributions and the audience for their engagement. Um, Thank you all for your time. We will be concluding this session three. Please let me know if you have any questions. Yeah, if there are any if there are no questions, please feel to drop off. Will be waiting until uh, fif- I guess 15 more minutes for for this to end. It's
Thank
until
you.
12:30 Central Time. So I'll wait until 15 minutes for paper ID 19. So feel free to drop off.
Thank you. Thank you for the opportunity. Thank you all.
Thank you.
Thank you, Karthik.
Thank you. Thank you, Dr. Murugan.
Thank you for the opportunity. Thank you all.
Thank you.
Hi, Karthik. Are you able to hear me?
Yes, I'm able to hear you.
Okay. So are we done with the presentations for this session?
Yes, we are done. I'll be waiting for the paper ID 19. We'll wait for 15 more minutes by Dr.
Okay.
Mr. Mohammed Fozil Rabi. So we'll wait for him to see if he shows up, and then we can conclude the session, like 15 more minutes.
Okay. Once it's complete, please again send us an email about the best presenter from your
Yes.
observations. And also,
Yes.
if a particular paper is not being presented, please also notify us via email which specific paper or papers has not been presented.
Yes. I already made a note of it in an Excel sheet. I'll be sending the sheet immediately after this call.
Okay. Thank you so much for your service.
Thank
Thank you.
you. Thank you.